Hello and welcome to another video. In this video we're going to be going over all the problems from the weekly contest 400. So let's get started. In the first one, you're given a string S and you want to simulate events. So if you have an E, a person enters the room and takes a chair, and L, a person leaves the room and takes a chair, freeing it up. So it drops off. So basically they can either come in, take a chair, or free it up, and you need to make sure that every person has enough chairs to pick up. So you kind of need to pick up like, okay, what's the most chairs that are going to be taken at one point? And so it's pretty easy. You just kind of simulate this and you just record how many chairs are taken, and the biggest number that happened is your result. So here you just take 7 chairs, so it's 7. Here so they kind of show you here. So you pick up a chair, drop off a chair, pick up a chair, drop off a chair, pick up a chair, pick up a chair, drop off a chair. And so the number of chairs, if you want to just think about it in terms of chairs, so you needed 1, then you dropped it off, then 1, dropped it off, 1, 2, 1. So the most chairs that were ever taken is 2. So that's what you return. In the third example, same kind of thing. So 1, 0, 1, 2, 1, 2, 3, and then drop off. So the most chairs that were ever taken is 3. And yeah, so pretty easy. You just add a chair if it's taken, drop off a chair if it's dropped off, and then keep track of the maximum. Not much to do there. Okay, so the next one is you have the days you're working and meetings, and they tell you how long the meeting is, and you want to return the number of days where you are working but there's no meetings, and meetings may overlap as well. So this one's pretty easy as well. So essentially for your meetings, this is basically just an intervals problem. You can just sort your meetings and merge all the meetings that happen that overlap. So if you have a meeting from like 2-4 and then another meeting from like 3-6 or something, you can just merge these into 2-6, right? So you can merge them, and then after all your meetings are merged, then you basically just look at the gaps. So in this first example, we have like 1-3, 5-7, 9-10. So you want to look at the gaps between the meetings and then the gaps on the end. So on the ends, you start at day 1, so if this is above 1, then there's a gap there, so you just record what that is. And then between all your meetings, you look if there's a gap. So here we're missing a 4, here we're missing an 8, and then here we have 10 days we're working, so there's no gap at the end, there's no gap at the start, but we're missing a 4 and an 8, so there's 2 days missing. So that would be the answer for that one. The second one, you can merge your intervals. So here we have 1 and 3 and 2 and 4, so we can just merge that into 1, 4. And we're available to work for 5 days, so there's a gap on the right, so we're missing day 5. And for the gaps between meetings, it's pretty easy. So like if a meeting ends, let's say it's like this, and it starts, I don't know, like 10:20 or something. The gap is just this number minus this number minus 1. So in this case, there's 7 days missing. So 3, 4, 5, 6, 7, 8, 9. I think that's 7 days. So yeah, right? 3, 4, 5, 6, 7. Yeah. Okay. So yeah, so that's basically it. And then the ends is straightforward as well. And then finally you look at like when did I end, and how far is that off from the number of days I had to work. So let's say I had 30 days I was working, I ended at 20, then we have another gap of 10. So hopefully that makes sense. So pretty easy. And then I just had my first end time start at 0, so that way if the first meeting starts at 1, and I do 1 minus 0 minus 1, there is no gap there. But if the first meeting starts at like 5, then I do 5 minus 0 minus 1, then I have 4, because I'm missing days 1 through 4. So a pretty easy one. Okay. And so for this one, you're given a string and it can contain stars. And when you have a star, you want to remove the smallest non-star character to the left. And if there's a tie, you can pick any of them. So this is kind of the tricky part of the question. So for in this example, since we have AA, BA star, when we hit the star, we can remove any one of the A's. And if you actually just so I always, I think I said a lot, like when you have these operations that you've never done, just kind of play around with it, see what happens, and then figure out, is there a best thing to do? Is there a shortcut or something? And so it turns out there is a best thing to do. So if I have a bunch of stuff like this, so first of all, let's look at a couple of examples. Let's say I have a bunch of letters like this, and then all of my letters that I'm removing are next to each other. Let's say something like this. So here it doesn't matter which one I remove, they're all going to give you the same thing. Let's actually use a number to demonstrate this easier. So let's just say we have like 1, 2, 3, or not 1, 2, 3. We have like 9 and 9, 1, 1, 1. so if we remove any one of these, it'll give us the same number, right? It'll always give us this. But what if we have some numbers in between these? So like I said, if there's numbers to the left of both, it won't matter. But what if there's some numbers in between the ones I'm removing? So for example, let's say I have like this. Let's say it's this. So I can remove 3 different ones. So let's do that and see what we get. So the first one, we'll remove the first one. Second one, remove the second one. Third one, remove the third one. And let's take a look at our numbers. So this number is the biggest, where we remove the first. This number is the second biggest, where we remove the second. And this number is the smallest, where we remove the third. And this is always going to be the case. They're either going to be the same, or the third one will be smaller, because if we have something like ABA, or whatever, BABA, if we remove this first guy, this B, so if we think of like most significant, like digit or so on, so let's just look at it in this way again. So the most significant digit is the most important. So if we remove this guy, then this digit will move up to like the second most significant digit. But if we remove this guy, then this digit will stay third. So that's kind of the idea, is you always want to remove the rightmost letter if there's a tie, because that will always be the best, or tie. And from the rest of it, it's pretty easy. So it's basically just like, I have a string. Every time I have a star, I need to remove the rightmost letter efficiently, because this is 10 to the 5th. So how do I do it? So you can think of 2 characteristics to sort on to remove for a heap. The first characteristic is going to be obviously the letter. That's the most important thing. So if there's a tie, then I'll do number 2. But the first thing is the letter. So we are going to put the letter into the heap. And the second letter, we want to remove the rightmost letter first. And in Python, there's only a min heap. So what we can do is we can just put in a negative index as well. So that way, if there's A's at a bunch of locations, let's say it occurs at location 0, 1, and 3, that means I'll have like A0, A -1, A -3. And so for this first thing, there will be a tie for all of them, but then for the second one, this is the smallest, so this is the one I'll remove first. So every time you hit a star, you're going to remove the letter with the biggest index. And so it's pretty easy here. Every time we have a star, we just pop. Every time we don't, we push the letter and the negative index. Then at the end, we have an array of letters and their index. So for example, let's look at this one. So we're going to have, and this isn't necessarily sorted, so this is like a heap, right? So we're going to have like A with 0, A with -1, B with -2. And this can be in any order, not necessarily sorted. So now what we want to do is we actually want to sort this on the index, but we actually want to sort it on the negative index, right? Because we want to maintain the order that we had originally. So this needs to be first, this needs to be second, this needs to be third. Now, like I said, this won't be in this order. It is in the right order in this case, but it won't be in the right order in the heap, almost, or very likely. So what you can do is you can just sort it on the negative index. So basically what that will do is it'll make the biggest negative index last. So like this will be last, because what this will end up being is it will sort it on, this will equal 0, this will equal 1, this will equal 2, and it will sort in increasing order. So this will be first, this will be second, this will be third. So after the sort, it will look like this. And then all we need to do is just take every single letter from these and join them into a string. And that's all we do. So we just take our heap, take all the letters, because now they're in the right order, and just join them into a string and return that. So not too bad. And finally, the last problem, also not a super hard one. So here, you have a array nums integer k, and you want to find a subarray such that the absolute difference between k and the bitwise and of the subarray is as small as possible. And so subarray is a contiguous sequence, and it's non-empty. And so basically what you can do here is you just pick some non-contiguous sequence like this, you get the and you want that and to be as close to k as possible, either above or below. So in this case, there's a couple. So these two and to 4, but also you can just take the 4 and that will and to 4, and 4 is the closest thing you get to 3. Okay. And yeah, there's probably some optimizations, but I'll just show you kind of like what I did. There's definitely some optimizations I could think, but yeah. In fact, yeah, there's probably some kind of sorting thing to like pick numbers that are close to it. Maybe that'll be, now that I'm thinking, that actually would be like a little bit better to do, I think. But the way I did it also works, but I'll go over that. So here we're going to pick 2, and that's closer to. And then here we can only pick this number, and that's 9 away, so we have 9. So the main thing to know for AND operations is when you AND a bunch of numbers, like let's say I start with A. If I AND it, if I keep ANDing it with more stuff, that result has to be less than or equal to A. So the AND of a bunch of numbers can't be bigger than the minimum number. Because if I have a small number like 1, and I AND it with stuff, any 0 in the 1 will stay a 0. I can't turn zeros into 1s. I can only turn 1s into 0. So I can AND it with like this, but that will still give me 1. So that's one thing to note, is that when you AND a bunch of numbers, the result can only get smaller or the same. Another thing is, let's say I have an addition. So I could do like let's say I'm making a window and I'm doing like, okay, I'm doing A plus B plus C plus D. And and this is my window, and this is good. And now maybe the window is too big, so I want to get rid of this A. Well, I can just subtract A, right? I can just be like, okay, let's just subtract A. Now this is my window. It's fine. The problem with for the AND, you can't do that. So if I'm calculating a value here, I can't just be like, okay, I have this value. Now I want to get rid of the A. Like you can't just get rid of an A. You can't just be. There's no like opposite AND operation, you know, to like get like if I just do this operation, I'll get my number back. At least I don't think so. So you can't do that. But what other way is there to do it? So instead of actually doing like these operations and then just like getting rid of the number, instead what we can do is we can store for every single bit in our window, we can store how many we have. So for example, let's say our numbers in our window is like 1, then we have like 2, we have 3, and like 5 or something. So what's going to be the count of all the bits in this window? So let's just say the 0 bit is the least significant bit, and then we'll go to the left. So for 0 bits, we have 3. For 1 bits, we have 2. And then for 2 bits, we have 0. Yeah. And for 3 bits, we have 1. And notice that if I actually AND all these numbers, this will be 0. Because in order for an AND of a bunch of numbers to be non-zero, I need every single bit in a column to be a 1. So like in order for this column to be a 1, all of these need to be a 1, right? All of these need to be a 1. So you can just store a bit count for all your bits, and then just go through them like I did here. And you can just say like, okay, well, if my window is 4 numbers, and I don't have 4 of this bit, then this bit in the result will be a 0. So you can kind of like just build your result from the bits. And because like I said, if I have some result, like let's say k is like 10, and my result is like 8, I know for sure if I keep adding numbers to this result, it will only get smaller. So there's kind of no point, right? So if your result is less than k, you actually wanted to shrink your window. For example, like here, like if I have, like, let's just go through this first example, I guess. So if we have like 1 and 2, that'll be 0. Now if I want to add 4 to this same window, I don't really want to do that because I already have a 0. So 0 ANDed with anything will just be 0. So instead, I want to get rid of these elements. So maybe I'll get rid of the 1. Now my window will just be the 2, which is just this. Now I can add the 4. And if I add the 4, then I'll have this. And same thing here. If I AND these, that'll be 0. And that's not good. So maybe I want to get rid of the 2. So then I'll just keep the 4. And so on and so on and so on. So essentially, anytime your number is too big, you're just going to shrink from the left. And when you shrink from the left, you can't do like a not AND or something. Well, I guess there is a not AND operation, but that's not going to like give you the original result. I don't think. So because that's the case, then yeah, I think it definitely won't give you the original result because like there's a bunch of different ways you can get the number back, I'm pretty sure. But anyway, so in order to get rid of a number from the left, I'm just going to take my bit counts that I have up here and just go through the number, and every bit that's in this bit count, I'm just going to decrease. And then once I got rid of a number, then I can actually calculate my AND total because I have all of my bits and I have the length of the window, and I can just say like, okay, for this bit, do I have the length of the window bits? If I do, that will contribute. If I don't, that will be 0, and so on and so on and so on. So let's look at the code. So essentially, we basically have a sliding window, we have a result, we have a left, we have a current total, and we get our number, and we go through our number, and we take all the bits, and if the bit is a 1, then we just increment the bit count of the whole window. Then, to actually get the total for all the ANDs, we just go through all of the bits, and we say if we have, for each bit, if we have the length of the window for that bit, then that bit will be a 1, otherwise it'll be a 0. And it's pretty easy to figure out what that will contribute. So if that's the 0 bit, it'll contribute 2 to 0. If it's the 1 bit, it'll contribute 2 to the 1, 2 to 2, and so on and so on. So you can just, so this is how you build up your total and then you say, okay, well, if my number is less than k, I want to shrink my window until it's not less than k. I want to make it greater than k, and I want to keep shrinking until it's, you know, greater than or like equal to k. Maybe you even want to keep growing. Maybe you want to even keep growing while it's like, even if it's equal to k, you probably want to keep growing, I think, because if it's already k, then why wouldn't you? I think that would make sense to me anyway. Let's see. Yeah, I guess either way works. But essentially, yeah, if your window is smaller than k, if you just keep adding things to it, it will only get smaller. So there's no point. So the only time you want to add things to a window is if the window is greater than k, because then you can make the number smaller. So it's basically just, it's kind of like the reverse. Instead of like, let's say you were trying to get the sum of a number, the sum of a bunch of numbers to be equal to k, you would subtract. Now it's kind of the opposite, where like, and you would subtract when your number's too big. Now it's the opposite. For an and, you're going to shrink your window when the number's too small, because and only makes the number smaller. So if the number's too small, we're just going to get rid of the leftmost element. So this whole thing, basically the same thing. And then we calculate our and again, and then we just maintain our result. And that's basically it. So the tricky part here is recognize I can't do like I can't just delete from the left with an and, right? I can't have like A and B and C and D and then just like get rid of it like I could with a plus or a minus. I can't just do this, but I can keep track of the number of bits I have, and I can manually calculate an and. And you can use this for other operations. If you can't just get rid of the number, just keep track of all the bits you have, which is pretty cheap because it's only O of 32, and then you can do that. Yeah, you can probably definitely make this smaller. Like, I don't think this is like the optimal solution, but this is like a decent one. And for a hard problem, I think it's pretty good. That like for a hard problem in the contest, which is also usually harder than most problems. So there is probably some other way to do it now that I'm thinking of, like sorting. Well, I guess sorting would be n log n, but it still might be faster because here, like we're like every time you do a total, it costs you 32 bits. The other thing is you probably, maybe this will be faster with a dictionary instead of an array. I'm not sure, because you go through 32 bits every time, where like maybe you have a couple bits. Depends on your numbers, I guess. So, but yeah, so essentially this is O of n and O of 1 space, because we're basically looping through all our numbers to get all the bits for number is O of 32, to get a total is O of 32, so it's all constant. And then space is O of 1, because for our bits we only have 32 of them. Okay, so let's go over the time complexity for the next ones. So this is a heap. So every single number we are adding to the heap. So that's going to be like, let's see. Okay, so the heap can be lengthwise. How long can it be? Let's say we have no stars at all. This is probably the worst case. Then we'll just keep adding to the heap. So that will be like n log n, I guess. And then we also sort our array at the end, which is n log n. So I think this is just n log n. And for the space, so same thing. If we have no stars, if we just have a string, then that will be O of n. So I think that's that. In the meetings, we're doing a sort, so n log n. We do the merge intervals, which is fine. That's like constant, or that's O of n. And then we do the this whole thing, which is O of n. So I guess we're merging intervals in here. So this is O of n, sorts n log n, and then actually having the meetings. So technically, probably you want to argue that like in these meetings, you probably want to make a copy, because I guess we're not merging in here directly. Yeah, we're not actually like merging anything. We're just sorting. So maybe it's like O of 1. Like we're merging on the fly. We're not actually like saving the result, because you don't need to. Like anytime you have a merge, you just combine them and you just store the end time. That's it. So we're not actually like modifying the meetings or anything. We're just sorting. So I think it's this. Yeah. I don't think I ran this one. Okay. Yeah. So then last one. So this is just a pretty easy O of n. And yeah, I think I did this kind of late. And I spent a lot of time just debugging mistakes. But I think honestly, if I was like not half asleep. I think this contest was honestly doable in like 30 minutes, which is really rare, like the whole thing. Because the first 3 problems were pretty straightforward, and this one is basically just like once you recognize it's just like you can store the bits. It's honestly not that hard. Like it's one of these, like, once you realize what to do, it's kind of more of a medium-ish problem, but it is kind of hard to realize what to do, so that I guess that's part of the hard problems. But most of the contest hard problems are like, even if you realize what to do, it still takes like a long time. Like the ones last week with the segment trees were like, okay, I know I need a segment tree and a bunch of other stuff. It's still going to take me like an hour probably. So yeah, definitely one of the easier contests as always. And yeah, I was saying, so I think a good goal to have is like do at least the first 3 problems in under 30 minutes. Because I feel like I was able to do the first 3 problems for the last, I don't even know how many contests. I want to say like at least 10 pretty fast. So that's definitely a good goal to have. And then the hard problem is just kind of variance. Like sometimes it'll be extremely hard, where realistically you're not going to be able to do it unless you're like a competitive programmer. This one's doable, so it kind of depends. Maybe like, I think for me, being able to finish them relatively quickly right now is probably like maybe 2/3 of them I can finish in a reasonable amount of time, and then 1/3 is like I have to like look up solutions or whatever, and it still takes like hours because they're just very, very hard. But yeah, hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.